The last speaker of this session is the Professor Matt Reece from Harvard. So his title is Cosmology and the String Swampland. Matt, you can recognize the time, right? The left one.
Let's see, this was this. Okay. Can you hear me okay? Is this working? Okay. Oops. Yeah, so I made my title a little bit longer because I want to talk about a few different things. Here's the outline of the talk. I'm going to spend most of my time talking about things related to the Swampland Program, which is the question of how can we constrain effective field theories using things that we know about quantum gravity. And there I'm going to talk about some recent papers I've written with Ben Heidenreich and Tom Rudelius. And then I want to give you a particular example of a theory that I think is constrained in this way. And these are theories of photons with very small Schicklberg masses. So I'll explain that. That's based on a paper that I'll post to arXiv this week. Then I'm going to talk about a couple of things that both involve dynamics of either axions or moduli. The first one will be about dark photon dark matter. And the second one will be about Higgs Finetuning. Okay. So what is the Swampland Program? This is a name that was coined by Kamran Vafa back in about 2005. And the idea here is that we know that there are examples of theories of quantum gravity that we can construct within string theory. But these theories often seem to have common features. They're not completely generic effective field theories. So you might have thought that any effective field theory that has a stress energy tensor can be coupled to gravity. That's true perturbatively. But it's not true that all of those things are going to be consistent theories of quantum gravity. And so we have various examples of theories of quantum gravity that we know exist. In some cases, they're continuous moduli spaces. In some cases, they're just isolated vacua. But we also know lots of examples of theories of quantum gravity that we think are inconsistent. And a classic example are any theories that have global symmetries. So there's a very old argument about this. In world sheet string theory, there are arguments due to Banks and Dixon from the late 80s. There's also a nice argument in terms of black holes, which is if you hand me a theory that you tell me has gravity and has a continuous global symmetry, I can construct black holes with arbitrary charge by throwing matter into the black hole. I can make a very big black hole with any charge that I want, and then I can wait and let the black hole evaporate until it's small enough that I stop trusting effective field theory. And at that point, I can now produce a large collection of black holes of infinitely many different charges that all have the same size, and that's thermodynamically problematic. So these arguments have been around for a while. One clear discussion of that argument comes in a paper from Banks and Seiberg back in 2010. But what Vafa and others started doing back in 2005 and 2006 is trying to more systematically think about what are the common features that we know seem to be shared by theories of quantum gravity, and can we produce some sharp conjectures about properties of all quantum gravity theories that let us draw a line between theories that we know are definitely inconsistent and theories that at least are potentially consistent. Okay. So why is this interesting for cosmology? It's interesting for various kinds of phenomenology, but I think particularly in cosmology, these swampland conjectures might play an important role. And one reason why you might think that is that there's a cosmological signal that's being actively searched for that can only be found in theories that have a somewhat surprising property, namely primordial tensor modes in the CMB can only be found if we're talking about conventional slow roll inflation in theories where some field phi evolves over a super Planckian distance. So the inflaton has to change its value during the course of inflation by an amount d of phi, which is bounded by the square root of r. So this is the Leith bound. And from the effective field theory point of view, you might be mildly concerned about this because you could say, why can't I write down Planck suppressed operators? But in fact, it's fine from the effective field theory point of view if you have a good approximate shift symmetry. And so an effective field theorist can't really say that anything is sick about a theory where a scalar field takes on values bigger than m Planck. But in quantum gravity, it seems to be much more difficult. And in particular, Aguri and Vafa conjectured that anytime you have a large distance in field space, you have a breakdown of effective field theory. So two kind of precise statements along these lines that were made back in those early papers in 2005 and 2006 are worth mentioning here. One is the weak gravity conjecture. This says that if I try to have a gauge theory and take the gauge coupling to be very small, I'll run into some sort of inconsistency in quantum gravity. In particular, it was conjectured by Arkani Hamed, Model, Nicholas, and Baffa that any theory with a small gauge coupling G will have an ultraviolet cutoff lambda, which is smaller than G times M Planck. And they conjectured furthermore that there must be at least one charged particle with mass below that scale. What we've recently found a lot more evidence for is that in fact there have to be infinitely many particles of different charges, a whole tower of particles that begin to appear at this scale. This is related to another conjecture that Aguri and Baffa made back in 2006, which was that any time you have a scalar field that travels a large distance in field space, d, you'll find a tower of light modes whose masses are exponentially small in d over m Planck times some coefficient. This coefficient is 1 or order 1 in most known examples. And that at least hints, again, at something being wrong with theories that badly violate the Lith bound. So we need to be a bit careful about quantum gravity when we're dealing with cosmology. So what I want to tell you about now is recent work that, that Ben Heidenreich, Tom Rudelius, and I have done that I think has clarified some of these statements and given us a little bit more insight into where they come from. And part of these arguments are based on another old idea, which is the species bound. So this is the statement that if I have a theory of gravity and it contains many weakly coupled degrees of freedom, it will have a cutoff that's low compared to the Planck scale. And there's a simple argument for that. We just look at gravitons coupling to loops of these weakly coupled particles. These will all contribute to the effective kinetic term of the graviton. And so roughly speaking, we'll get a correction to the Planck scale that's proportional to the number of degrees of freedom. And so in a theory in 4 dimensions, what this means is you expect the fundamental cutoff of quantum gravity theories to be smaller than m Planck divided by the square root of the number of degrees of freedom. So Gia Diwali, for instance, has written a lot about this based on the idea that if we add 10 to the 32 weakly coupled degrees of freedom, we would explain why the cutoff is at the TeV scale. But it's a more general statement that we expect to hold in any theory of quantum gravity. So what seems to be the correct way to think about many of these swampland conjectures is they're about towers of particles that exist in theories of quantum gravity. In particular, the version of the weak gravity conjecture that I think is very well supported and can be rigorously proven in perturbative worldsheet string theory, which of course is not all quantum gravity theories, but it's an interesting subset of them, is that you have infinite towers of charged states of infinitely many different possible charges, and the mass of those particles is bounded by their charge times the Planck scale. If you have such a tower, and here's a simple example, we have a particle of charge 1 with mass e times m Planck, where e is a gauge coupling. We have a particle of charge 2 with twice that mass, and so on. This kind of thing happens, of course, very naturally in Kaluza Klein theories, where you have a tower of KK modes, but it happens much more generally in theories of quantum gravity. If we just start counting all of these particles, we would infer that there's a low cutoff by these species-bound type arguments. And the number of particles below the cutoff is given by the maximum charge in such a tower. And so when you plug that into this formula, you would infer that if I have a small coupling E, I have a fundamental cutoff where gravity stops making sense. Everything becomes strongly coupled, and that happens at a scale e to the 1/3 times m Planck. Now what's interesting is you can derive the same scale from different assumptions. So given this tower of particles, instead of looking at corrections to graviton propagators, we could look at corrections to gauge boson propagators. And so again, we'll have lots of particles running in a loop, but they'll contribute differently now. Each particle will contribute its charge squared to the kinetic term of the photon. And again, we can add up this entire tower. If we add everything up to the scale Q, and we ask, at what point does that explain the smallness of the gauge coupling E? So we sort of imagine starting from a strong coupling in the UV, we integrate out this tower of states and we get a weak coupling in the IR. You would want to stop adding up these particles when the charge Q is of order e to the minus 2/3. But in fact, that leads you to exactly the same conclusion about the cutoff. So the interesting thing is, given this tower of states, which kind of saturates these conjectures, weak gravity type conjectures, when you start computing loop effects, you find that they naturally drive the theory to strong coupling so that both gravity and the gauge coupling become strong at the same scale. And that scale here was e to the 1/3 times m Planck. But in fact, this argument works for any gauge group. So we could have a non-abelian gauge group, we could have particles in arbitrary representations that saturate some bound, and we'll again find that the non-abelian gauge coupling and gravity become strong at the same scale. So this leads us to suspect that a lot of these conjectures are really evidence of a different kind of statement, which is a statement that theories of quantum gravity that have weak coupling always begin with strong coupling at some energy scale that's kind of universal. So everything is strongly coupled. And then you have towers of weakly coupled particles, and as you integrate them out, you get to weaker and weaker coupling in the infrared. And that certainly seems to be true in a lot of examples. So what we realized is that we could explain some of these old observations of Aguri and Vafa based on this different starting point of thinking about a universal strong coupling scale. So Aguri and Vafa told us that if you go large distances in field space, you have towers of particles that become light in an exponential manner. But they just observed that this was exponential in lots of examples that they found in string theory, and they didn't really know why. What we can do now is instead to say, suppose I just have some scalar field, and I'm going to imagine going large distances in the scalar field, and that as I do so, some tower of particles becomes light. So I'll have my field phi, which is a scalar. I have this tower of particles psi. They have a mass that depends on the value of phi. And what I want to imagine is there's some point in field space for phi where these particles are all becoming light. And in general, I could decide that that point is what I'll call phi equals 0. And that these particles are becoming light in a linear fashion as I approach that. That's just a way to parameterize the field. If I then add up loops of all these particles coupling to phi, I find that they generate corrections that go like this. The 1 over k of phi comes from canonically normalizing my field. And if I ask that these loops are driving the scalar field to strong coupling at the same scale that gravity is becoming strongly coupled from the species bound, I can in fact derive the form of this kinetic term as a function of phi. And so we just add up this tower of particles, and we learn that we want the kinetic term to be related to a sum over all the particles up to the cutoff of this derivative of the mass with respect to phi squared. If I'm imagining everything goes linearly, that behaves like this. And I end up deriving that the kinetic term should go like m Planck squared over phi squared. So this assumption of a universal strong coupling scale lets us derive as an output that the form of the kinetic term for the scalar looks like this. It looks like m Planck squared divided by phi squared times the derivative of phi squared. Now this happens in lots of examples. Again, that's what motivated Aguri and Vafa originally. If you just take a theory of GR, compactify it on a circle, you get a lower dimensional theory with a scalar radion mode, and its kinetic term has exactly that form. But the interesting thing is that for Aguri and Vafa, this exponential behavior was kind of a guess. It was an observation. And here we're deriving it from something that seems a little more fundamental, which is a universal scale of strong coupling. We can apply a similar argument to other fields, like axions, that have a compact field range so that I can't go infinitely far. And you get another interesting conclusion out, which is that, again, assuming a universal strong coupling scale, you derive that if your axion field goes a very big distance in field space, bigger than m Planck, a typical particle in your tower will have a mass changing by an amount bigger than the cutoff. So this is, again, I think a thing that we had observed in various theories, and now we have, I think, a better understanding of where it comes from. It suggests that anytime you have a super Planckian field traversal, you have an order 1 fraction of all the modes in your theory moving above or below the cutoff. And so you should worry about whether you really have a valid effective field theory at all. So I think all of these things give us some reasons to suspect that theories of large field inflation that badly violate the Leith bound are things that you should be suspicious of. Of course, to be consistent with data, you might only need to mildly violate the Leith bound. And it's a lot harder to make statements about kind of order 1 factors. Okay, so in this way, I think what we've shown is that many of these Aguri and Vafa statements seem to have their roots in something maybe more universal about strong coupling. One loophole I should briefly point out is that all of these bounds depend on the field space distance as measured by the kinetic terms of the field. They make no reference to the potential. And so there might be ways to wiggle out of these bounds if you have a theory of inflation where the potential forces you to take a long path, but the actual geodesic distance between where you start and where you end up is shorter. So we're certainly not at the point yet where we can claim that all theories of large field inflation are in tension with these sorts of conjectures. But there's a lot of interesting activity exploring how you might evade some of these bounds. Okay, so now I want to give you an example of a theory that I think is ruled out by these kinds of quantum gravity considerations, which are theories of very light Stuckelberg masses. And this is something that has kind of bothered me about quantum field theory for a long time, which is that if I have an abelian spin 1 boson, I can just add a mass for it, and it doesn't hurt anything. Right? So in our universe, we don't have a good field theoretic argument that the photon couldn't have a mass. We have phenomenological bounds, which are extremely strong. But you could always say, why don't I just add a photon mass to the Lagrangian, and I can't stop you from doing it. I think that in quantum gravity, that's no longer true, that masses for photons are not allowed to be arbitrary. And one way to see that is to write the mass in Stuckelberg form. So instead of just writing a mass, let me introduce a scalar field that shifts when I do a gauge transformation. I can then dualize the field theta that I introduced that shifts into a two-form field B. So I can just take the Hodge dual. And now if I apply weak gravity conjecture-like arguments to this B field, it tells me I shouldn't be able to have a B field by itself. There must be things that are charged under it, and the things that are charged under a two-form are strings. And so the suspicion then is that any consistent theory of quantum gravity that has a massive gauge field also has string-like objects where as you wind around the string, this scalar that was eaten is going around a circle. And what the weak gravity conjecture suggests is that the tension of these strings is bounded by the product of F and M Planck. Now, if I have an ordinary mass from a Higgs mechanism rather than a Stuckelberg mass, these strings are perfectly innocent. We just have strings in the abelian Higgs model. They're semi-classical objects. You go to the center of a string and the Higgs field goes to 0. And that's just part of your effective field theory, and it doesn't tell you anything deep about the ultraviolet. But I think there's a subtle difference between the Higgs mechanism and the Stuckelberg mechanism, which is what happens in the core of the string. So in the Higgs mechanism, there's a point in field space where the Higgs VEV is 0 and the photon mass goes to 0. But in the Stuckelberg mechanism, there's nowhere in field space where the mass is 0. And in fact, you might think the difference is the existence of the Higgs boson, the radial mode of the field. But when you find examples of Stuckelberg masses in string theory, there always is a radial mode because the underlying theory is supersymmetric. And so whenever you have an axion-like field, you also have a saxion partner. The special thing that happens with Stuckelberg masses is the point in the middle of the string where you would have said the Higgs went to 0 and the photon mass goes to 0 is a singular point in field space. So the kinetic terms are badly behaved in precisely the logarithmic kind of way that I was mentioning before. And that's kind of the invariant physical distinction between the two. And in that case, these strings always have some fundamental meaning, and their tension always behaves as some kind of ultraviolet cutoff on the consistency of the theory. So if I have a photon mass, it's a product of two numbers, a gauge coupling E and some dimension full scale F that you can think of as the coupling constant of the two form if I'm writing the mass as a BF term, or the period of the axion if I'm thinking of it as eating an axion. And so what I'm saying now is that either limit where I try to make this mass small is sick in quantum gravity. The E goes to 0 limit is the weak coupling limit of an ordinary gauge field. And the F goes to 0 limit is a weak coupling limit of a different kind of gauge field, a two-form gauge field. And in both cases, quantum gravity is going to resist our efforts to make those things weakly coupled. So depending on which one I send to 0 faster, I could get a different sort of bound on what the UV cutoff is. But in either case, if I have a very small mass, I have some sort of UV cutoff. And this is a plot of what that UV cutoff would be as a function of the mass of the photon and the coupling. So if I have an order 1 coupling, like for the standard model photon, and I have a bound on the mass, like say bounds from fast radio bursts on the photon mass, my theory would have a cutoff not far from an MEV, and it would be inconsistent. Or if I have a dark photon that I'm generating from, say, inflationary perturbations, and I want my cutoff to be above a TeV, I would need a coupling bigger than, smaller than 10 to the minus 3. But in fact, I want my cutoff to be even higher than that. If I'm generating it from inflationary perturbations, I want it to be bigger than Hubble. So we get interesting constraints both on the standard model photon having a mass. This is completely ruled out unless we have the quantization of electric charge wrong. So if you're looking for a loophole, maybe the charge of the electron isn't 1, maybe it's 1 trillion, and that would be incredibly weird. But then you could have a Higgs with a tiny charge that gives the photon a mass, and I can't tell you it's inconsistent with any of these conjectures. It's not very plausible, but I don't think it's logically inconsistent. Then we could also talk about dark photons. People have proposed many experiments searching for dark photons, things like DM radio, looking for dark photons as dark matter. And again, it's an interesting theory from the effective field theory point of view because it's technically natural to have a small mass. But the only mechanism I'm aware of in the literature for actually generating dark photon dark matter with the right relic abundance relies on inflationary fluctuations. It relies on having a high Hubble scale, and so as I was mentioning, that's in tension with the kinds of UV cutoffs you get from these arguments. So in fact, they would have said anything above about a micro EV. This is Graham, Martin, and Rajendran who derived this dark photon abundance from inflationary fluctuations. They would have said they could obtain the right relic abundance anywhere above a micro EV, and I would say that given these bounds that I think hold in theories of quantum gravity, the mechanism only works for masses above about 1/10 of an electron volt. So part of the parameter space is inconsistent. There's also a substantial part of parameter space where people are building experiments, but nobody has a model for the right relic abundance. And so now in the last few minutes of the talk, I want to change gears a little bit and stop talking about quantum gravity and start talking about some theories with interesting cosmological dynamics. And the first thing I want to mention is a model for how to get the right relic abundance of dark photon dark matter over a wider range in theories that I think are at least potentially consistent with these quantum gravity bounds on dark photon masses. And this is work that I've been doing with Pratik Agrawal, Naoya Kitajima, Toyokazu Sekiguchi, and Fuminobu Takahashi. And the idea is simple. It's based on a well-known mechanism, which is that if we have a coupling of an axion to a spin 1 field through a phi FF dual type coupling, then if that axion is time dependent, if it's oscillating, you can have certain modes of the photon go tachyonic. So a given helicity of the photon will have a range of momenta k over which the time dependent term that you get from the axion dominates and gives you an effective tachyonic mass. And so you get exponential growth of those particular modes. And so if you have a theory of a massive dark photon and it couples to an axion in this way, essentially what you can do is use the misalignment mechanism to store a lot of energy in that axion. And then as the axion starts oscillating, you convert a lot of that energy into dark photons. And so this is capable of populating a large part of the dark photon dark matter parameter space. You get photons with kind of a typical momentum that's set by this coupling constant beta times the axion mass. So you want the photon mass to not be too small compared to that, or these will be highly relativistic. So there's a bit of a coincidence problem. But for a certain range of parameters, you can generate dark photons, which are initially mildly relativistic, and then they redshift, and they just behave like matter. And you can efficiently deplete the axion abundance, which is this curve, to be a small fraction of what it would have been, while the dark photon relic abundance can be a significant part of what would have been the axion relic abundance. And so you can populate dark matter in this way. Now it's important that these photons not thermalize, which means you need the coupling to be very small. But again, there is a part of parameter space that I think is consistent even with these quantum gravity bounds on Stuckelberg masses that I was mentioning before. Okay. In the last few minutes, I want to just briefly mention another topic, which is even less related to the other things I was saying, but it does involve, again, dynamics of an oscillating field that's driving interesting behavior in the early universe. And the idea here is to try to say something new about the Higgs fine-tuning problem in terms of cosmology. So I'm not going to try to solve the Higgs fine-tuning problem, but suppose we just live in a universe where the Higgs boson potential happens to be tuned. I think that's the simplest explanation of what the LHC is telling us so far. We just have a mild fine-tuning. It could be a theory like mini-split supersymmetry. And the question is, how do we test that? And usually we test it by looking for particles at the LHC, and if we don't see them, we say, well, the theory must be fine-tuned. But the interesting thing about cosmology is it could maybe give us a positive signal of fine-tuning. There could have been something that happens if you have a fine-tuned theory that would not have happened if you had a completely natural theory. And the picture looks like this. We have a Higgs potential here. This is our universe with our Higgs potential. But imagine changing some parameters. If we're fine-tuned, then if you change parameters a little bit one way, you'll have unbroken electroweak symmetry. If you change them a little bit the other way, you'll have badly broken electroweak symmetry. And the interesting thing is, cosmologically, this changing of parameters could have been done for us by the vev of some other field phi, which I'll call a modulus. Again, I think this is well motivated in top-down considerations. These kinds of moduli are all over the place, and string compactifications are really any construction with extra dimensions. And in this context, fine-tuning is the fact that the point where the modulus, the point where the global minimum lies, happens to be near the point of marginal electroweak symmetry breaking. So the modulus could have had its minimum way over here, or way over here, but it happens to be there for no good reason. It's just a fine-tuning. And the interesting thing about that is it can lead to dynamics. And so this is work with Mustafa Amin, Gigi Fan, and Kaloyan Lozanov. So we simulated the system, and we found that when you have a fine-tuned potential like this, as the modulus oscillates, it's sort of going back and forth between the theory wanting to be broken and wanting to be unbroken. When you're in the broken phase, you start exponentially populating Higgs modes through tachyonic particle production. And these back-react on the modulus and lead to this highly fragmented picture. So what would have been a coherently oscillating field is now broken up. It has excitations of many different momentum modes. And so you get very violent dynamics, and we've simulated this in the case where you have no fine-tuning, nothing interesting happens. In the case where you have fine-tuning, you get this kind of picture. And the hope is that maybe that gives you a signal to look for. So I'm going over time. Let me just briefly mention there's a burst of gravitational waves that happens when this field fragments. The simplest version of the model would put that at too high a frequency for LIGO to see, and also probably too low in amplitude due to redshifting of the gravitational waves after they're produced. But as a general idea, I think this is really worth exploring more. If there could be an observable signal from the early universe that would tell us something about whether electroweak symmetry breaking is fine-tuned. Okay. So just to wrap up, I guess the theme of this talk, which is kind of veered from topic to topic, is mostly that I think we should take seriously what top-down theories like string theory tell us. I think that a lot of things that look fine in effective field theory, like tiny photon masses, are actually sick in theories of quantum gravity. And I also think that string theory gives us these ingredients like axion fields and moduli that could play really interesting dynamical roles in cosmology. And of course, there are many theories that already rely on these to do interesting things, but I think the space of things we can do with these fields hasn't been fully explored yet. Thanks.
Thank you again for a very nice talk. So we have some time for questions or comments. Okay, Marco?
Can you discuss a bit more what scales you have in mind?
Can you use the microphone, please?
So for the last application you were discussing, there was no indication of scales. So can you give a bit more details?
Yeah, so what I have in mind is that this modulus is something coupling through Planck suppressed operators. So the field range in the modulus is something like M Planck. The mass of the Higgs and the mass of the modulus are both something like 100 or 1,000 TeV. So I'm imagining something like mini-split SUSY. So the natural scale of SUSY breaking is a couple orders of magnitude above the weak scale. We happen to be living in a place where there's a cancellation between, where this term happens to be much smaller than its typical value, and the Higgs mass happens to be only 100 GeV, but the typical scale is a few orders of magnitude larger.
Any other questions? Okay, behind.
So, sorry. So your field here is essentially a curvaton field. Don't you run into problems with non-Gaussianity?
So you're talking about this scenario?
Yes, exactly.
There are various things that you could do. Right, so one possibility is that the field phi simply is the inflaton, and so this is after inflation and it has just started oscillating. It could be that it's some other Yeah, there's a bit of an initial conditions problem if it's not the inflaton, in terms of why do we start. If you have a lot of radiation around, it will give you thermal corrections to this potential and kind of possibly pose problems for this mechanism working at all. So the case where it's not the inflaton, I think, needs some model building to explain the initial conditions to make this dynamics really work, and then probably also to explain things like non-Gaussianities or isocurvature corrections. So yeah, I haven't totally thought that through, but I think the case where this is the inflaton just could be the minimal version of the scenario and doesn't have those problems.
Any other questions? Okay, it seems not. Then let's thank all the speakers in the first session. We'll have a 30 minutes coffee break and we'll be back to the session again at 11.